Okay, so we've been talking about the operation of subdivision of simplices and chains, and the kind of the point about this, as we mentioned at the beginning, is the point about subdivision is just to make our simplices smaller. The next thing we need to do is to be a bit more quantitative about that, and so try and describe exactly how much smaller the simplices get when we subdivide. So we'll have this definition. Okay, so we're going to consider a linear simplex because the vertices A0 up to AR actually let's make it AN linear n simplex in delta n. We put the diameter of U is just going to be the maximum of the distances between vertices. Okay, so I've defined this to be the maximum distance between vertices. It should be kind of if we just draw a picture, say here. It should be clear, actually, this is the same as the maximum possible distance between any 2 points in the simplex. Okay, but let's say, yeah, so that's kind of visually fairly obvious, but we should really prove it, and along the way of proving it, we'll prove a little extra result that's also going to be useful. So yeah, so if we've got any points x and y in the image of this map U, so the distance between any 2 points is less than or equal to the diameter. And we could consider the special case where y is actually the central point. We get this extra factor, n over n plus 1 times the diameter. Okay, so that's a little bit less than 1. I mean, not a great deal less than 1, actually. We don't, which is going to mean that we actually don't divide up. The reduction in size on subdivision is not actually that great a reduction, but it is a reduction by this factor, n over n plus 1, which is at least strictly less than 1. So x can be written as the sum from I is 0 to n of xiai, and y is going to be y0a0 up to yn an, which is this is the sum from j is 0 to n of yj aj. Okay. And here these are and these coefficients, of course, are all non-negative and sum to 1. Okay, so these are the points in our simplex. Okay, so now I've got this equation here that x is the sum of the xiai's, and I can multiply it by this equation here that the sum of the yj's is equal to 1. So I find that x is the sum of both I and j, from 0 to n, xi, yj, ai. Just like I say, multiplying this equation here by the equation sigma j yj equals 1, I end up with this. And in the same way, I can multiply this equation that y is the sum of the yj aj's by the fact that the sum of the xi's is equal to 1. So I get this equation here, and this gives me that so I've got the xi, yj in both cases, and then you've got an ai minus aj. And then by a kind of triangle inequality, okay, so these xi, yj's, they're non-negative, so I can just sort of take them out. So I've got the sum of the xi, yj's times norm ai minus norm aj. Okay, so okay, but then yeah, so here this norm ai minus norm aj, that's less than or equal to the diameter. Okay, and then this is the sum over ixi times the sum over j yj times the diameter of u. But sum of the xi's is 1, sum of the yj's is 1, so that's equal to the diameter of u. Okay, so this is showing us that the distance between x and y is less than or equal to the diameter. In other words, maximum possible distance occurs when you're just looking at the vertices, which, as I say, is geometrically extremely reasonable. But now let's we also said in the statement of this lemma about the special case where y is the barycenter. So that's just the case where yi is equal to 1 over n plus 1 for I. Okay. So that tells us now that the distance from x to y is less than or equal to the sum from I and j from 0 to n of xi divided by n plus 1 times so let's just fix an I and look at all the possible j's. So the term for j equals I is 0. Okay, of course, if we take fixing I and then look at the possible values of j, one of those terms is going to be equal to 0 when we take j equals I. The norm of ai minus aj is just 0. And the other n terms are less than or equal to xi over n plus 1 times the diameter. So just taking if we just fix an I and look at the remaining terms j, right? So you've got you've got n terms, each less than or equal to n over each less than or equal to xi over n plus 1 times the diameter. So altogether, what we've got is less than n xi over n plus 1 times the diameter. And now the sum of the xi's is equal to 1, so this is n over n plus 1 times the diameter of u. Okay, and that's what we were supposed to prove. Okay, so we took any 2 points, the distance is at most the diameter. From any point to the barycenter, the distance is at most n over n plus 1 times the diameter. Okay, now let's just generalize slightly the definition we had a moment ago. Okay, so previously we defined the diameter of a single linear simplex in Rn, but now we suppose we've got a linear combination of them, then we're just going to put that the diameter of u is just the maximum of the diameters of the various various individual linear simplices that occur in this linear combination. Okay, and let's also just put Cn is n over n plus 1, so this is this number that we saw in the last claim about the distance from the barycenter. And let's just note that that's 1 minus 1 over n plus 1. So we find that C0, so these are increasing sequence, always strictly less than 1. Okay, so now we need this lemma. If U is a linear simplex in Rn, then I want to claim that the diameter of the subdivision of U is less than or equal to this constant Cn times the diameter of U. And okay, so the diameter of any zero simplex is just 0, so there's nothing to prove in that case. Okay. Yeah. So yeah. Okay, so we consider a single linear n simplex. So so let's say any simplex V in subdivision of U is beta W for some in okay, so how do you get simplices in the subdivision of U, right? Remember the way the subdivision works, you subdivide the boundary of U and then you join everything to the barycenter. Okay, so now so so let's consider a pair of vertices in beta W. So one of them is the barycenter. Then the distance is less than or equal to Cn times the diameter of U by the previous lemma. Because the previous lemma said that you've got any point whatsoever in this simplex U, then the distance from the barycenter is less than or equal to Cn times the diameter. Otherwise, you've got two vertices in. Otherwise, you've got two vertices in V in W. And so then the distance is so W is a simplex occurring in a subdivision of U composed of delta I, and that's an n-1 simplex. Okay, and so by the induction hypothesis, you've got less than Cn-1 times the diameter of U composed of delta I. Okay, but well, Cn-1 we know is less than or equal is strictly less than Cn, and the diameter of U composed of delta I is kind of fairly obviously less than or equal to the diameter of U. Okay. And so that's, either way around, you get less than or equal to Cn times the diameter of U, and that's what we were supposed to prove. Okay, so now we've shown that this subdivision operation, it shrinks diameters by this factor of Cn, which is strictly less than 1. And that means if you want to make if you want to get U to be extremely small, you keep subdivide as many times as you like. Each time you get a factor of this Cn, and powers of Cn tend to 0. So if you subdivide enough times, you can make your simplices arbitrarily small.